Hi everyone, welcome to Mostly Math. Today we'll be talking about another result from the following book, An Imaginary Tale by Paul J. Nahin. Fantastic book, all about complex numbers. This one from a more historical perspective. And here's what we're going to do today. We are going to evaluate the following integral from 0 to infinity with respect to x of 1 over 1 plus x squared. I'm sure you all already know the value of this integral. The purpose of this video is not to find out what the value is, but to evaluate it in an unusual way using complex numbers. Not the way that you might have seen it though in terms of the residue theorem, but a more historical method before the complex analysis methods were created. First step, if you saw this integral, was to immediately recognize it as the antiderivative of the arctangent function. To recognize this antiderivative as the arctangent function. So which is the arctangent of x evaluated at infinity and 0. Of course, inverse tangent of 0 is 0, so that bottom limit goes away. Comes inverse tangent of infinity, which we know has a limit of pi over 2. From looking at the graph of the arctangent, asymptotes here, and pi over 2 and minus pi over 2. This is the inverse tangent of x. That's pretty easy. This is an elementary integral. You would learn this in a first semester calculus class. What's important is not the value of the integral. The point of this video is to compute it using an unusual method. In particular, we are going to decompose the integrand by partial fraction decomposition and see where it goes. So for this video, we are going to assume that the person that's trying to derive the value of this integral has no knowledge of the arctangent function. So this derivation will be useful if you know complex numbers, but for some reason you don't know what the arctangent function is. Historically, this is not why this method was considered. There were some elementary pioneers in the field of complex arithmetic, basically before people knew what complex numbers were. Of the form, a plus bi, of course. People didn't really accept that these numbers were real in the time that this derivation is taken from. In particular, some specific dates from the book. We have the year 1719. People didn't really understand complex numbers very well, so I'm going to use some hand-wavy arguments in the proof that we're going to present as follows. The first step is to write the integrand. First, let's talk about the factor 1 over 1 plus x squared. Let's write this as 1 over x minus I, x plus I. We can do this because if you multiply it out, you'll see that it's true. It's also of the form a squared minus b squared is equal to a minus b, a plus b, of course. This is just an elementary usage of the difference of squares. So everyone agrees that we can do this, at least if you accept the existence of the imaginary unit. And now we are going to decompose this in terms of partial fractions. So we have the partial fractional decomposition. God, that's hard to write, isn't it? Which of course everybody abbreviates PFD. We are going to guess that it's proportional to this 1 over x minus I minus 1 over x plus I. Why would we guess this? Well, we've done partial fractions before. We think it's going to be this. Maybe there'll be a minus sign, but let's see what we get. If we do this, it's x plus I minus x minus I over the denominator And we see that the x's cancel away, and we get 2i over the denominator. So now we can write our expression here as 1 over 2i times 1 over x minus I minus 1 over x plus I. And now you can see that we've split up a quote-unquote a difficult integral, at least if you didn't know the arctangent function, into a series of simpler integrals, which we are assuming that we know how to evaluate for the purposes of this video. Just 1 over 2i, and to go from 0 to infinity with respect to x of 1 over x minus I minus 1 over x plus I. And we're assuming that in 1719 they knew to recognize this as the logarithm, since we have integral of dx over x minus a for some a is the same as integral with respect to the variable x minus a over x minus a, which we know is the log of x minus a. We're not going to write the absolute value signs for this video since we're not going to be rigorous anyways. If you're not familiar with this more physicist method of substitution, all I've done is let u be x minus a and du is equal to dx, of course. This is a great example to test your understanding of the physicist's method of substitution. Now that we know that, we can simply write what we have here as 1 over 2i times a difference of logarithms evaluated at the endpoints. Log of x minus I minus log of x plus I at infinity and 0 respectively, of course. And now we can proceed as follows. I guess we don't need this anymore, do we? So we can use the property of logarithms to combine them together, namely log of x minus log of y is equal to log x over y. We can use this elementary property to combine the logs. Just 1 over 2i log of x minus I over x plus I, evaluated at infinity and 0. Why am I using this property to combine the logs? Well, you'll see right now. So here's what we're going to do. We are going to consider that x is now a complex number, since it has to be, since we're subtracting I from it. And to evaluate the infinite limit, we're going to assume that the absolute value of x is much greater than the absolute value of I, which is 1, of course, since I in the complex plane lies on a circle of radius 1. So it has to have a magnitude of 1, of course. This is going to evaluate the infinite limit. So if x is much greater than I in magnitude, we can simply ignore the i's. So it becomes 1 over 2i. The first term becomes log of 1, which of course is 0. And the second term, we shouldn't have any problem plugging in 0 into this expression. So it becomes log of minus I over I, which is of course log of minus 1. And now we're actually going to use another property of logarithms. We're going to use the property that log of 1 over x is equal to minus log over x. Now, why am I using this property? I'm using this property to get to the correct answer. And I have to use this property because this function here, of course, has to be the arctangent, and there's a branch cut. So there's potentially multi-valued functions for this, which of course they didn't know about in 1719. So I'm using this property to get the correct value. And let's go ahead and do this now. This allows me to actually take the minus sign, put it inside, and of course minus 1 over 1 is still minus 1. So I can just change that minus sign to a plus. Of course, 1 is the only value that this works for. -1 is. So it works out in the end. And this, again, has to do with the branch cuts in the complex plane and so forth, which we didn't know about in 1719. All right, let's proceed. All right, so we now have 1 over 2i log of -1, which we're going to write as 1 over 2i log of e to the I pi. Since, of course, e to the I pi is -1, we go around pi radians to get to the -1 value. So e to the I pi is -1. Note, I don't have to add 1 to both sides to get the more beautiful version of Euler's identity, e to the I pi plus 1 is equal to 0. No, this is crap. You never use this in mathematics. Never. It's always e to the I pi is equal -1. So don't tell your friends that this formula encompasses all the 5 important constants of 0, e, I, pi, and guess 1 is there. Yeah, it does. But I can also add a 0 to this expression here. And then it also has the 5 constants, but it's not as cool. So just a short rant. Don't use this. Use this. Or you can write e to the 2 pi I equals 1, which is much better. And it tells you that 2 pi is better than pi, because this formula tells you that if you go halfway around the circle and then go across the diameter of the circle, you get to where you started, which is stupid. This one tells you that if you go all the way around the circle, you get where you started, which makes a lot more sense to me personally. Hopefully you agree. Sorry for the digression, but let's continue. I mean, this topic requires its whole other video by itself, when you define the number tau to be equal to 2 pi, and then argue that tau is better than pi, which I believe that it is, but I'm not going to do that here. All right, continuing. So, log of e cancels out, so it just becomes I pi over 2i, which is, of course, pi over 2. So we get our correct answer. I just wanted to note that if I hadn't used the property of the logarithm here, I would have gotten minus pi over 2, which corresponds to a non-principal branch of the arctangent function. In particular, I just wanted to note that you may have noticed that this function is equal to the arctangent function itself, since we had 1 over 2i log, I'm just going to write as z minus I over z plus I here. We can actually multiply the argument of the logarithm by 1 over I, which is the same thing as minus I. If we do that, we have minus I times z minus I, which is equal to, see, it's so difficult, isn't it? Same thing. 1 over I. Okay. 1 minus iz is now on top. And let's see. Did I do this wrong? Okay. Okay. The bottom one here should be the same. D minus I z plus I. 1 over I. T minus I. Yeah, this should be correct here. It should be 1 over I. My arithmetic is failing me today, but it's going to be this 1 over 2i log 1 plus iz over 1 minus iz. You can figure out my mistake later. I'm just not in the mood to do arithmetic now. Sorry, which we recognize, of course, as the inverse tangent of z. So this is just an expression for the inverse tangent, which we have covered in a previous video when I could actually do the arithmetic. Sorry for the inconvenience. And yep, that pretty much completes the presentation today. Just wanted to note that we did some non-rigorous things here. We evaluated the upper limit, assuming that one complex number was greater than the other, or at least appealed to their magnitudes being greater, which is not entirely correct. And of course, we used the branch cut incorrectly. But I just think it's cool to note that you can indeed perform the original integral by partial fractions if, for example, you forgot what the arctangent was. So if you enjoyed this, want to see more math, especially complex numbers, please subscribe, tell your friends. See you next time.